Welcome everyone, this is lecture number 10 on semantic segmentation. We have already completed the introductory session in the deep learning part. We'll now advance towards more applied and more specific applications of deep learning, as we can see here in this list. Semantic segmentation is, as you can see, a classification on the pixel level. So while we in the beginning classified whole images to contain cats and dogs, we now want to classify each input pixel as belonging to output classes such as the street or cars or pedestrians, buildings and trees and all these things. There's a difference that we have to see here between semantic and instance segmentation. So in instance segmentation, we really want to discriminate between separate instances of a certain output class. So for pedestrians, for example, here, we want to have an output that lets us discriminate these. Although they are belonging to the same class. So today's goal is to learn about our network architectures that we can use for semantic segmentation. And before we do that, let's talk about how to represent the output. So an input is an image or an image sequence like we had before, but what are the outputs? So we could think of an output as either being a one-channel, same width and height like the input, but this one channel now contains pixel-wise IDs of the object. So 0 could be, the background, 1 could mean dog, and 2 could mean cat. Now the more common, let's say, representation of the output is a tensor that has C many channels for C many classes that we can encode. And again, the same width and height like the input image. Now, for example, this could be the same 3-class output for background or unknown dog and cat. And so you have ones everywhere where those pixels belong to the background, the dog or the cat. Before we get into the actual model architectures, let's have a look at your or possible data sets, the data sets that we want you to work on in the assignments. First of all, there's the PASCAL visual object recognition data set that was published quite a while ago. So PASCAL was or still is a consortium of many research groups. They all wrote an application to the EU, who then funded this excellence network. And it's a challenge that every year got more images and data for the competition, and so you always have like a year here given. And for 2012, for example, we have almost 10,000 images, 20 classes that are encoded, and you have those objects manually segmented. And PASCAL was then extended by other groups. For example, PASCAL-Context here has 16,000 images in over 400 classes, and I think even larger images. And you could find this data set here behind this link. So I think we are reaching the image size and also data set size that your consumer grade hardware can actually swallow, let's say, RAM wise. And but anyway, so COCO, for example, is still something I think that could work with your hardware, has 80 classes and over 200,000 images. Cityscapes is something that you can. So if you have a good GPU, you could try. It comes with so-called fine annotations and coarse annotations. This relates to how well those objects are manually segmented. 30 classes, German cities. And something that's very specific, and obviously, if you look in different domains of applications, you'll find those data sets as well. So for example, cell tracking or cell segmentation is a very specific task. And I'm showing you that because one of those algorithms that I'm introducing to you has, or was proposed using only that data set. Yeah. One last thing before I show you the network is performance metrics. So we so far have only looked at classification and object detection tasks, and we have been using metrics like accuracy, for example. So the number of correctly classified samples. Now, here in segmentation, we classify each pixel, but using the pixel accuracy, so the number of correctly classified pixels may not be a good performance metric. So for example, here in this task, we have a satellite image as an input, and we want to segment out those ships and boats here. But since almost the entire image is background, even producing a black output will produce quite high accuracy values, so that's kind of misleading. What you should be doing, and what people usually do in segmentation, is a measure that's called IOU, or intersect over union. So here you have your output per class, and you look at how many pixels actually overlap with the ground truth. And then you divide that number of pixels with the union, so the sum of those pixels. Yeah. So sum of both outputs minus the overlap. Yeah? And if you have your new model, and you apply your or you train it on a data set that others also have been using, you can compare your results as this website, paperswithcode.com, is doing. And so you can look at how you compare to the others and how the field itself has developed. I invite you to click on that link and see for yourself. Now, let's have a look at architectures. So the most simple, the simplest idea would be to have like a static input of a given size, maybe 100 by 100 pixels or so, and use a convolutional network that just maps to a one-dimensional output that represents the, let's say, likelihood of your center pixel here to belong to, I don't know, a certain class, right? You could have also a C-dimensional, so for C many classes, output for the respective likelihoods that this center pixel now belongs to background dog or cat. Yeah. And then you could slide that over the input and like successively fill this output. Okay. But this has a number of disadvantages. And what do you think these are? Okay. So first of all, it is quite slow because you have the sequential processing. It's also inefficient because remember the network, the ConvNet, encodes the input image into like a hierarchy of features, of image representations, right? And from these representations, it kind of classifies. Now, running the network over and over again doesn't reuse these features, right? So we have to compute them again and again and again, although neighboring outputs may still use the stuff that has been computed in the run before, right? And it's also potentially inaccurate because it doesn't, or it can't use the full image context. It only has a small window it relies, or it bases its output on. Okay? Now, to kind of give you like an intermediate step towards getting better, we could use a fully convolutional network, which basically says, okay, we have an input that has a size width by height, and then we use convolutional layers with the appropriate, settings for the kernel size and the padding and the stride to obtain feature maps that do not decrease in size, such that in the end we have a classification layer that produces the output, and the output has the same size as the input, right? So what do you think, what kind of problem would this design or this architecture solve, and what disadvantages do we still have to cope with? Pause the video, think about what this could be, and I'm going to solve the question now. Okay, so obviously the network now sees potentially the entire input. I'm saying potentially because given your choice of what kind of convolutional kernels you have and what how many layers you actually configure your network to have, you may not see everything, right? So an output pixel may not be able to rely on the entire input, but potentially you can design the fully convolutional network such that each pixel can see all input variables. Now, the biggest disadvantage here is that this network is just super huge. This is a monster, and may take a long time to train, and may also lead to overfitting because there's so many parameters involved. So to alleviate this last problem now is we just use less parameters, and we design the network such that it looks like this. So the original resolution now is downsampled into a smaller representation. So width and height is way smaller than the original. And to then obtain an output that has the same size, we have to upsample again, right? So in this middle part, we save parameters, yeah? So which operations do we know that implement downsampling? I think we have discussed a couple of those, and we have not yet discussed what upsampling methods they are, and we will discuss it in the following slides. But first, this question: which operations do you know that lead to oversampling? To downsampling. I'm not going to clear up this question because we have the session, and I need some questions for the quiz later. So, but how can we upsample? So one of those most simple things is nearest neighbor upsampling. So given an input, 2x2 input, and a desired output size 4x4, nearest neighbor sampling or upsampling now looks at the nearest neighbor. That's what the name already tells you. The nearest neighbor for a given output position, the nearest input position, and takes that value from there, right? So it's like you take that 2x2 patch and like warp it over this bigger output, and then so this one position here would extend over these 2x2, this 2x2 block, and the 2 would extend over the other 2x2 block here, and so that's nearest neighbor upsampling. And you can have many different variants of interpolations. So, for example, bilinear interpolation, which basically says, okay, for each position in between the two given ones here, we like linearly interpolate between those values, right? And there are different ways you can align these corners, so you get a slightly different values for here, and also like trilinear interpolations and bicubic interpolations. So there's like a whole bunch of different methods that you can use. To be honest, I think the most popular or like the most common versions are nearest neighbor upsampling followed by convolutions, but I may be outdated already. Okay, so the next two are Max-Unpooling and Transpose Convolutions. Let's have a look at Max-Unpooling. So one of the ways we can downsample is by using Max-Pooling, and this is done by looking at a certain sub window, maybe a 2x2 or 4x4 region in the previous layer, and then take the maximum of that, and then write that in the output layer. So, for example, if we have a 4x4 matrix with these given numbers, and we use a 2x2 window, then for this 2x2 block here, 42 is the maximum, and we write it down here. And for this block, for non-overlapping blocks, we then look at these four values, take the 39, write it down here, and all these different blocks are processed the same way. Now, we also remember those indices. So where did we get the maximum from? Because in Max-Unpooling, we need these indices to then fill the output in the upsampling step with those respective values, right? So let's say in this output layer, we have a 2x2 matrix with these kind of values, and we want to upsample these. And what we can do is we just take the indices that were determined in the max pooling step in the respective layer in the downsampling step, and we write these values into these positions. So this helps in in producing much more detailed and less fuzzy boundaries of objects. Another way to do upsampling is so-called transpose convolution. So remember what convolution is. Convolution takes in a, let's say here, 4x4 matrix, and using this 3x3 kernel, then uses dot-wise products, and then sums up everything and writes the result in this next layer. So here it's a 2x2 output, and depending on how you configure that conv layer, for example, using no padding and using a bigger stride, you can drastically reduce the size of the subsequent layer. And to revert that process, you can use transpose convolutions. So these work like that. You have a given input, and your output needs to be larger, right? So what you do is you take in every value from the input layer, multiply it by your kernel, which, by the way, can be learned, right? So can be optimized for. And you write the result into your subsequent layer. And now you repeat that with the next input. And in some areas, these two results will overlap. So you sum up for each of these positions all the results that overlap. Okay, so this is a very simple kind of way to have an upsampling step with learnable parameters. And the reason it's called transpose convolution is because of this. So let's reduce this to a one-dimensional case. If you have two functions, one is with 4 numbers and one is with 3 numbers, the convolution, right, is just the dot product of these. And every time you have already computed the dot product, then you shift the one function, and then you produce a new dot product. This time b times c, b times x, c times y, and d times z are summed up to produce the next output, and so on. And you continue that, right? Now, and that's not limited to the one-dimensional case. That's actually also what we do in the normal 2D or 3D or whatever D case. You can write your convolution as a matrix vector product, right? So, for example, in our image case, we have a matrix that looks like that. So we have entries that in the first row appear in the next row, but in a shifted kind of version of that. And that kind of matrix is called a Toeplitz matrix. And the positions of these parameters here are determined by, well, by your configuration of your conv kernel, of the stride, of the padding, and all these things, right? And so if this, for example, is your input, multiplying this matrix to that input actually performs a convolution, because remember, convolutions are basically dot products. And so that's something that you already should know. Multiplying a vector by a matrix kind of projects that vector down to another vector space that can be arbitrarily sized. So for example, here we have an m-dimensional input and an n-dimensional output, and that convolution kind of reduces the size. Now we can also arrange that differently and take, for example, the transpose of that matrix, which now maps the output back into the input space. And you should already know that because we used that in backpropagation, right? When we had the gradient propagated up until a certain, let's say, m-dimensional feature layer, and then we want to distribute this backpropagated gradient down to the next layer, which may have a different size. So we take the transpose of the weight matrix, remember? And so this is just to explain a little bit why it's called transpose convolution. You will see many different names for that operation, which almost always mean the same. Deconvolution, which I don't like because it is not the signal processing deconvolution, like the inverse of the convolution process. So don't use deconvolution, but it's called upconvolution or unconvolution or fractionally strided convolution. So there are many words for that, but basically it's just under the hood. It's just multiplying a matrix to the input. Okay. UNet is now the network that I wanted to introduce you to. You are supposed to implement UNet for the assignment, and it's basically a very simple, kind of progression of 2, or let's say 3 main steps. The first step is what you already know, a convolution. So the input, with a fixed size of 572 by 572, is convolved with one kernel and the next kernel, and then it that reduces the size of the feature map to 568 by 568. And then the second kind of base operation is max pooling. So you already know what that is. That reduces the size of the feature map by a factor 2 in both dimensions. So we end up with a feature map of 284 times 284. Then again, we continue the convolution and the max pooling, convolution, max pooling, convolution, max pooling until we have quite a small, spatially small feature map of 28 by 28 pixels, but it's quite deep, right? It has many channels or like features here. Now, so this is like the downsampling path, and we'll now complete this with an upsampling. So look at those blue boxes here. So this deep but like small feature map is then upsampled, and then you see that white box here. That is the concatenated feature map of the previous step, right? So the not downsampled version. So you combine low resolution information with a higher resolution information, and then you combine these into a joint feature map with a convolution operation again. And you continue that upsampling step. I think they use interpolation plus a convolution. And you combine those low resolution feature maps always with the higher resolution feature maps from the corresponding step before. And now you can see that the sizes don't quite match. So here it's 136 squared, and this is 104 squared. So the authors propose cropping that feature map to the correct size so that they are actually able to concatenate these feature maps. Yeah, and so those feature map sizes are determined by your choice of the convolutions, your stride configuration, your stride setting, or your padding setting. So I think if you can arrange that in a smart way, you don't actually have to cut. But the authors, I think, do that for also another reason. So look at the last step here. There, the crop is quite small with respect to the original size, and so there's a slight not even a slight, it's a big mismatch between image locations here because, right, so the blue feature map here corresponds to the entire image, and the white feature map here is basically only, let's say, 2/3 of the entire image. And that is because this was used for the cell segmentation task, and most cells appear in the center. And so I think that was kind of the idea behind cutting or cropping away so much. So UNet was proposed in 2016 or 17. It's still heavily used. I think it's a neat kind of architectural design. It's easy to re-implement, and that's why you have to do that too. It improves on the localization accuracy of fully convolutional networks. Has used heavy data augmentation, although, and that is the only thing I don't like about that paper, it wasn't tested on a common data set, common like a real world object data set like Pascal. Okay. UNet, as I said, was tested with those cell segmentation tasks, but it also has found many applications outside this domain. So, for example, for 3D reconstruction, so you can have like objects segmented out of multiple recordings. It also has been used, for example, for voice separation. So audio can be represented as so-called spectrograms, which is a function over 2 dimensions. So one is time, obviously, and then the second is frequencies, right? So it's like a frequency. So yeah, it's like the spectrum over time, okay? And these images then can be processed in such a way that you can separate different voices, and that there in this paper UNet was used. So that just gives you like a slight hint about how variable and versatile UNet can be, and segmentation networks can be. That was it. I hope you enjoyed lecture number 10 on semantic segmentation. You have learned about how to downsample, how to upsample. You have learned about how to quantify the performance of your segmentation network, and you've learned about architectures. Concluding with UNet, that's what you have to implement. I hope you have fun with the assignment. See you all next week. Bye.